Amazing developments are taking place in China, where scientists are diligently engaged in the production of clothing that makes individuals practically invisible. For an extended period, invisibility has been regarded as equal to superhuman abilities such as extraordinary elasticity and immense strength, like the renowned Fantastic Four heroes. However, at present, human invisibility is nearer to reality than to the realm of science fiction, and it is entirely due to what scientists refer to as self-adapted photochromism, or SAP for short. SAP is quite clear when you analyze the words. It is merely the capability of an object to wrap light in a manner that mirrors the items nearby. Wang Dongxiang, the lead researcher, stated in an interview with China's Science Daily that this technology could render a person effectively invisible when applied to clothing. This means that although it may not be entirely transparent as most people envision invisibility, it effectively causes the object to vanish. This ability for active camouflage is found in many creatures, such as the well-known chameleon. The reptile utilizes specialized cells known as iridophores and chromatophores to reduce its visibility. Iridophores of the past hold small nanocrystals that reflect varying wavelengths of light. Therefore, when they are densely arranged, it reflects shorter wavelengths associated with blue and purple colors. However, when they are packed loosely, vivid hues such as red, yellow, and orange become apparent. When combined with chromatophore cells that hold pigment, chameleons can effectively reflect nearly any color from the light spectrum. As an example, blue light bouncing off the iridophores and going through yellow pigments in other cells will cause a green appearance. Some aquatic animals, such as octopuses and squid, can also attain near invisibility using the same principle. But why is the anatomy of these animals relevant to modern scientists trying to replicate invisibility? Well, it's because self-adaptive photochromism works on the same principle. Instead of Mother Nature's specialized cells, SAP relies on photochromic molecules, which are molecules that reversibly change their structure and color upon exposure to light. Now, when you pack multiple of these molecules become a material, it gains the ability to change color and essentially becomes invisible under the right light. However, if achieving invisibility were that simple, we would have cracked the code decades ago. For most of the late 19th to mid-20th century, scientists that observed photochromic effects were simply aided by its ability to change color. In 1867, Carl Julius Fuchs first reported this phenomenon when he noted that a solution of orange tetracene lost its color in daylight and regained it in the dark. Nearly 100 years later in the 1960s, William H. Armistead and Stanley Donald Stuckey would commercialize that knowledge to make the first commercially viable photochromic lenses for eyeglasses. Self-adaptive photochromism wouldn't become a viable means to mimic active camouflage till more recently in the 2010s. I know you're probably asking what changed. Well, it was the discovery of Donner acceptor Sternhaus adducts, DASAs. Unlike traditional photochromic molecules, DASAs exhibit what scientists call negative photochromism, which is a fancy way of saying that they are typically dark-colored but turn significantly lighter or colorless when exposed to light. Another reason I think the discovery of DASA was a major game. The change was because of how it reacts strongly to visible light. Before then, traditional photochromic molecules were known to mostly respond to UV light, which doesn't carry as much information about color in our visible environment. As a result, the molecules could only change their absorption slightly, meaning colors would change hues at best. DASAs are one step up because on exposure to light, the linear colored molecules adopt a cyclic colorless form, creating a significant absorption gap. In plain terms, that means if you mix these molecules with specific dyes, they respond by blending with objects of that color. For example, if you take a DASA molecule in its original black or very dark linear form and expose it to red light from a red background, the DASA molecules will undergo linear to cyclic isomerization. This isomerization will then make the material unable to process light at that wavelength, allowing the object to reflect that color back and blend with the background. That's why the discovery and development of DASA materials is so exciting in the scientific world. Before then, replicating this camouflage skill in man-made systems was a bit more complicated. Unlike naturally occurring molecules or evolutionarily perfected specialized cells, artificial systems have to first recognize the background they're trying to imitate, process it, simulate, and change. As a result, this four-step process typically requires high-definition cameras that capture light and transform it into digital signals. These signals then trigger external stimuli such as heat or electricity, which induces color switching. That brings us back to recent Chinese studies on SAP using materials that leverage negative photochromism. In one experiment, researchers were successfully able to create active camouflage by placing an SAP solution-filled container in environments with red, green, or yellow colors in the background. Within 60 seconds, the solution changed colors to match its surroundings, rendering it invisible. Amazingly, this team of researchers, led by Wang Dongxiang from the University of Electronic Science and Technology of China, have also recently moved beyond liquid solutions in a publication from late 2024 in a journal called Science's Advances. The team published their findings on incorporating SAP materials like polycaprolactone into flexible films and coatings. The material then adapted its color to blend seamlessly with the surrounding environment within a 30 to 80 second time frame. I think this breakthrough is especially relevant because it shows that self-adaptive photochromism has practical applications beyond solutions in a lab. Imagine being able to mass-produce military uniforms using this technology to effectively render troops invisible to the enemy. Considering recent speculations of an impending world war, this type of innovation could be a game changer on the field. Armies with chameleon-like camouflage abilities could effectively march through enemy territory, unseen and unopposed. They'd blend seamlessly with copper-red desert sands and lush green forests, and by the time the enemy realized they were at the gates, it'd be too late. I think it also helps that SAP materials display quick color adaptation, making it promising for real-time camouflage. With a 30 to 80 second window, it's incredibly fast at mimicking its environment, giving troops enough time to escape detection. Besides its quick performance, another reason SAP materials are so impressive is that they function effectively across a wide temperature range from -20 degrees C to 70 degrees C, -4 degrees F to 158 degrees F. That makes it ideal for missions in diverse environments, experiencing weather extremes. It also makes it suitable for other industries with varying temperature demands. Beyond the tactical advantage on the battlefield, the mainstream use of self-adaptive photochromism would have other effects. Thus, by carefully creating invisible spots on the chessboard pattern surface and altering the magnetic field, they can control what direction the colloids take. As a result, the particles flow around these hidden spots like water around a rock. I think the best part is that these magnetically engineered obstacles don't affect the speed of the particles. According to one of the researchers, Anna Rossi, we have also shown experimentally that if the obstacle shape is chosen correctly, the size of the obstacle does not matter. It can be any size and the particles still arrive at their destination in time. That essentially means this principle doesn't just apply on a micro level. You can scale it up and, in theory, make any object invisible from a tiny pebble to a jet. So, what do you think about a future where invisibility suits either using photochromic molecules or chimera metamaterials are possible? Do you think it's something that would have a net positive impact on our world? Or are the ethical and safety concerns too much of a risk? Let us know in the comments. Don't forget to like, subscribe, and turn on notifications for more in-depth looks at the tech shaping our future. Thanks for watching.